In 4.5, we'll look at situations involving inclined planes. Inclined planes are any surfaces that are at an angle to the horizontal. So for example, a hill, a ramp, any kind of incline fits into this category. The angle of inclination is here at the bottom of the ramp or the surface and where it reaches the horizontal, and I've called that theta here. If we consider an object moving on an incline, maybe a box sliding down a ramp, you'll realize that since the box moves along this surface, we'll have acceleration and velocity parallel to the surface, the normal force perpendicular to the surface. If we included friction, that would also be parallel to the surface. So most of the vectors that we're seeing are either parallel or perpendicular to the surface. In fact, the only one that isn't is the force of gravity. So because of this, it will greatly simplify our problem if we use a new coordinate system. We're going to use a rotated coordinate system so that the x-axis is parallel to the incline, to the surface of the incline. So that becomes our x-axis, and then the y-axis is perpendicular to the incline. Now, I've decided, or it's kind of conventional, to leave this as positive y. You can choose whether positive x is up or down the incline. So make sure you indicate this on your diagram so that someone reading your work will know that you're using a new coordinate system and which directions are positive. It makes sense to me to use down the incline as positive actually because this looks like our standard xy coordinate system where this would be the first quadrant. This greatly simplifies our problem because now we have an object moving along an incline, so the net force in the y direction is equal to 0, and we only have an acceleration in the x direction. If we use a regular up and down coordinate system, we'll find that we have many components in all directions. So we do have to add components onto gravity when we go on to solve problems on an incline. So let's draw in those components. I'm going to draw them in here. Now I want to find where the angle is in this diagram. So if I extend this down, this is a right angle triangle since this is the horizontal and gravity is vertical. So this is 90, this is theta. So in here, this angle would be 90 minus theta. Now this is a right angle here as well, so the angle in here is 90 minus theta, which is theta. So our angle of incline is actually right here in the triangle. So I'll just erase this and then we can find the components. Alright, so I've drawn it a bit bigger and erased the other writing now that we know that theta is in the inside of the top corner of this little triangle here. So we can find the components of gravity. If we look here, this is the y component in this y coordinate direction. So that's FGY, and it's adjacent to theta. So this is going to be FG cos theta. Then if we look at this component here, this is opposite to theta. It's in the x direction. So this is going to be FGX, which is equal to FG sine theta. So the components are maybe a bit opposite to what we've seen many times. So we need to remember here that our y component now is actually cos theta and our x component is sine theta due to the orientation of the angle of inclination on the incline. And this is the basic object moving along an incline diagram with no friction. If there's any friction or applied forces, we can add them into our free body diagram and then solve as we did for other dynamics problems. So we want to write out F net x and F net y, evaluate if it's accelerating or not, and then solve for any unknowns. Okay, let's look at some examples. Example 16, a brick of mass 1 kilogram slides down an icy roof inclined at 30 degrees to the horizontal. What is its acceleration? Okay, we'll ignore friction at first. That's what it's kind of indicating by the icy roof. And this is an incline, so you can draw your incline. It doesn't matter which orientation it's facing. And we have a 30-degree incline. And then the brick is on the roof here. There's no friction, so we just have the force of gravity, Fg, and then the normal force, Fn. And let's use the simplification of this rotated coordinate system. So I'll use down the incline as x positive, and then up away from the incline as the positive y direction. So this is the free body diagram for the incline without friction. And now I need to break up gravity into its components. So I showed you why the angle here is also in between the components there. So that's 30 degrees, and then this is going to be FGY, and this component is FGX since it's also parallel to the incline. The block does not move up or away from the incline or into the incline, so the net force in the y direction is 0, and again, this is one of the main reasons that we'll use this rotated coordinate system. However, it does accelerate down the incline, so the net force in the x direction is equal to max. Notice that there's only one component here of a force that's in this x direction. It's just this x component of gravity. So we'll have Fgx equals max. I'm going to switch sides. So max equals Fgx, or max equals Fgx, remember it's opposite to the angle here, so this is going to be sine. So it's going to be Fg, which is mg sine theta. And notice that the mass cancels here. This result is independent of mass. The acceleration equals g sine theta for this brick moving down the incline without friction. And then we can plug in, we have 9.8 meters per second squared sine 30, which is 4.9 meters per second squared. Example 17, an object is held at rest on a smooth surface at a 25-degree angle to the horizontal by a rope parallel to the surface. If the tension in the rope is 450 newtons, what is the mass of the object? And ignore friction. Okay, so I've drawn the incline diagram again here. This looks very similar to the last question, but now there's a tension force that's holding the mass up on the incline. Again, we'll use the same coordinate system. And since this mass is at rest, we have the net force in the x direction and the net force in the y direction equal to 0. Since we know the tension force, we can use the x direction this time in order to find the mass of the object. So in the x direction, I've drawn an arrow down here. We have only this x component of gravity, Fgx, and the tension. So Fgx minus Ft equals 0, which is Fg sine theta, since it's opposite again, minus Ft equals 0. So first we can find the force of gravity. It will be Ft over sine theta, 450 newtons divided by sine 25, which is 1,065 newtons. And then to find the mass, we can do Fg over g, just dividing by g here, 1,065 newtons divided by 9.8 newtons per kilogram, to get 109 kilograms as the mass of the object. Example 18, a 15-kilogram box is released on a 32-degree incline and accelerates down the incline at 0.30 meters per second squared. Determine the friction force impeding its motion and the coefficient of kinetic friction. So this time our incline diagram now has the normal force, gravity, and kinetic friction, which is opposing the motion. Since it's sliding down the incline, the kinetic friction is going to be up the incline. And we know it's kinetic since it's moving. And we'll use the rotated coordinate system again. We have a 32-degree incline, and we're told that it accelerates down the incline at 0.30 meters per second squared. So we're going to need to use kinetic friction here, which is mu k Fn, and eventually find friction in order to plug in to find our acceleration. So we know that we'll need the normal force. So let's look at the y direction. It's not accelerating in the y direction, so the net force in the y direction is 0. And then we have Fn and Fgy here in the y direction. Fn minus Fgy equals 0. So Fn equals Fgy, which is mg or Fg cos theta. And we could find that number now if we wanted. So that's 15 kilograms times 9.8 newtons per kilogram cos 32. So otherwise you could save this expression to plug in later if you wanted to solve a different way, but I'll find that value. So the normal force is 125 newtons. Notice that it's not equal to the weight in the case of an incline, right? It's actually lower than the weight because of this component of the normal force in that vertical direction. All right, so now let's look in the x direction to find the acceleration. Net force in the x direction equals max, so we have max equals this x component, fgx, of gravity minus the force of kinetic friction. So let's plug in for that. I'm going to have max equals mg sine theta, since it's opposite to the angle in the x direction, minus mu k Fn. And then we can find this force of friction. So we're actually just asked for friction first. So let's just leave that as Fk and solve. So I'll end up with Fk equals mg sine theta minus max. Okay, and then we can plug in here. So that's going to be 15 kilograms times 9.8 newtons per kilogram sine 32 minus 15 kilograms times 0.30 meters per second squared to give the force of friction as 73.4 newtons. And then, so that's the first part, what was the friction? Now we want the coefficient, which we could have found here, but since we have friction and the normal force, let's just solve for the coefficient using Fk equals mu k Fn. So I have mu k equals Fk, friction, over the normal force. 73.4 newtons divided by 125 newtons gives 0.59, which is quite high, for the kinetic friction between the box and the surface. Example 19, on an icy day, you worry about parking your car in your driveway, which is inclined at 12 degrees. Your neighbors' driveways are inclined at 6 degrees and 9 degrees. Which driveway is safe to park in if the coefficient of static friction in each case is 0.15? Would you have to repeat your calculations for a truck with similar tires? What about a car with studded tires? So on the driveway, it's static friction which is keeping the car at rest, since we know it's at rest and it's static friction here. So one way to solve this question other than checking all of the angles is to find the maximum angle theta max at which you can park on your driveway safely, and then see which driveways are under that criteria. So if we're looking for the maximum angle, we're going to take the limit of static friction at that angle. So we'll use maximum static friction equals mu s Fn, and theta is our unknown. Since we want the car to be at rest, we have the net force in the y direction equals 0, and in the x direction equals 0, and we will need both to solve. Let's look at the y direction first. Just the normal force, and then this y component of gravity, again in that y direction. So Fn will equal Fgy, which is mg cos theta. Then in the x direction, the net force, again 0 of course, so I have just this x component of gravity, Fgx, and the static friction. So Fgx minus the maximum static friction equals 0. So here for Fgx, this is mg sine theta minus mu s Fn equals 0. So mg sine theta minus mu s Fn, I'm plugging in here, mg cos theta equals 0. And what we want to solve for is theta here. So one thing to notice is that it's difficult to solve for sine and cosine to isolate them when we have both terms in this equation. So I'm going to cancel the mass because it's in both terms and g. So essentially we're dividing both sides by mg. And now I have sine theta minus mu s cos theta equals 0. And rearranging further, I can have sine theta over cos theta equals mu s. Now, often in this course, you're going to see this relationship, sine theta over cos theta. So you might not have known this already to solve this question, but I want you to remember it from now on, that sine theta over cos theta is equal to tan theta. So we have tan theta equals mu s. And now I can find this theta, which is the maximum angle. Theta max will equal tan inverse or arctan of mu s, which is tan inverse of 0.15. And if you do this, you'll find an angle of 8.5 degrees. So this is the highest angle of driveway that is safe for the car to park and not move, not roll down the driveway. So the question was, which driveway is safe? Well, 12 degrees, no, it's too high. And 9 degrees, no either. It's still greater than 8.5. So this means that only the 6-degree driveway is safe. All right, so there were 2 questions now. Would you have to repeat your calculations for a truck with similar tires? This is getting at a vehicle that's heavier than the original, so higher mass. Notice this was independent of mass, so no, we would not have to repeat it for a more massive vehicle. This result that we have is independent of mass, which is good so that any massive vehicle can park on the driveway safely. However, would you have to repeat for a car with studded tires? Yes, we would, because the studded tires would change the coefficient of friction if the tires were different between the tires and the driveway. And if they're studded, that would add friction. It would definitely make a higher angle, a higher maximum possible angle.